this lecture, we are going to continue to look at regression diagnostics. So in the lecture 6, we talked about the crime dataset. So we are going to look at the association between crime and then the other factors. So we are going to look at how the other factors affect the crime, and we use the linear regression in here. So as I talked in the last lecture, we have the when you run the linear regression model, we have three parts of the output. So we have analysis of variance, which gives information about the significance of the model. And the second part is the model fit. And the third part is the parameter estimates. So for analysis of variance, we see that the p-value for f statistic is less than 0.05. Means that we reject the null hypothesis. When here the analysis of variance part, the null hypothesis is that the model is the only intercept only model, and the alternative hypothesis that the one of the regression coefficient is at least one of the regression coefficients not zero, which means that the model is significantly different from the null model. And then here we reject the null hypothesis, and then it means that there is evidence that our model is significantly different from the null model. And then R square is 0.84, which means that in this model, the variability of the 84% of the variability of crime is explained by these three variables. And this parameter estimation, we can get the fitted regression model, and then they are all significant. And the interpretation is that for probability means that given that all other variables are fixed, one change of probability will increase on average 17.68 crime. So, as I said, we have to do the regression diagnostics. Check linearity is, we need to check the linearity and check the outliers. For checking linearity, we can use the scatter plot and residual plots. And then check outliers for the linear regression model is we look at the absolute value of student test residuals. And you can use a scatter plot and residual plots to look at how many of them exist, and then you can use the output option to check which observation has the large student test residual. And then for this lecture, we need to check the other assumptions. So check normality, the constant variance assumption, and then check the leverage points and the influential points. So check the normality assumption. We can use the product univariate. So you can use the product univariate to test normality of residuals. So we create the crime one rest as before. which contains the output from this linear regression and the diagnostic information, and we store residual R. This is the raw residual, and R student, the student touch residual, named by RSTU, on this output data set, which is the crime 1 res. And then we can make a plot of the QQ plot, and then histogram, and then create the kernel density curve, or for normality, and or you can specify the normal option in the QQ plot to check normality by throughout the QQ plot. And then this mu and sigma request a normal distribution reference line with mean, estimated mean of R, and variance of estimated variance of R. And if you look at this curve, then if you look at this, the blue curve is the usual normality curve, and the density curve is this red. So the fitted normal curve is this blue, and this red one is the non-parametric density curve. And this is the histogram, and they are very shaped. So we can think that the normality assumption for residual is the reasonable. This normal QQ plot, you can see that the reference line is means that if observations lie in this reference line, that they are normally distributed, and then these observations are normally distributed. And then you can see that the most of the observation lie in this reference line. Then you can also check that the normality assumption is reasonable. And also testing whether it is a little bit problematic, but you can look at the test, all the p-values are greater than 0.05. So I think this should be cannot. So we cannot reject the null hypothesis and conclude that residuals are normal. And then another way is that you can use this normal to plot normality plot and QQ plot from the following code. So this is only available in the SAS-Descartes version. So you can use this R for residuals, and the NPP that represents theoretical normal probability. And so the normal probability part is which x-axis is our normal cumulative distribution, and y-axis is the empirical cumulative distribution of residual. And then this QQ plot represents theoretical normal quantile. Then this can produce as the QQ plot. So for this one, it's residual for normal distribution, and the normal cumulative distribution and cumulative distribution of residual, they are in the straight line, which means that the assumption for normality is reasonable. So this is another way to check checking normality on here. For normality assumption of error. So actually, if you just want to estimate the coefficient, this normality assumption is not necessary. However, we need this one because we want to do an inference on the regression coefficients. But as sample size goes large, this inference tends to be robust even without normality. So this normality assumption error is, I would say, the least important assumption in this regression model. So if your sample size is large enough, then you can perform the inference. So the next one is we will check the homoscedasticity. This is called homogeneity of variance. The error variance should be constant. So this is one of the main assumptions for ordinary least square regression. Then which means that there is no pattern to residuals plot against the fitted values. If there is a pattern, that there might be a problem. And then if we call the residual variance as heteroscedastic when the variance of residuals is non-constant. So variable of constant residual non-constant means that variance of residuals variance of each residual is different. So for example, if you have the residuals, and then the variability between observations is, say, increasing over or your predictor or value increases, or your predicted value fitted value increases, and in that case you can say that the variance of ratio is not constant. So the common used method to check this assumption is that make a plot. So the plot is we make a plot residual versus fitted values. So this is the plot, the predicted value versus the residual, and then you can see that there's no specific pattern, so that we can think that graphically homogeneity of variance assumption is satisfied. And then we can do formal test for heteroscedasticity, which is called Y test. In the test, the null hypothesis is that the variance of residual is homogeneous. And then, if p-value is less than 0.05, we need to reject the null hypothesis and then say that there's a strong evidence that the variance is not homogeneous. And then we can use the spec option on the model statement to obtain Y test. And then when you look at the Y test on here, then the p-value is greater than 0.05, then we cannot reject the null hypothesis and conclude that the variance of residual is homogeneous. So when you have non-constant variance issue, when you have the heteroscedasticity, we can use some methods. So you can use the more complex models. You can use, say, polynomial models. Polynomial means that you consider put the quadratic term or the cubic term. And then also you can use weighted least squares, which means that you put the weights on in your least square estimation, or you can transform x or y so that we can have the good linear regression fit. So transformation of x or y variables are commonly used to deal with, you have the nonlinear pattern, which is curvature, the non-constant variance of errors, residuals. Then common use of transformations are square root, square, log, or reciprocal. The general rule is that if you have nonlinear pattern but constant variance, you may want to transform of an x. And if linear but non-constant variance, it means that there's a problem with the response, error term, which means that the problem of the response, so that we transform the y. And if we have both of them, we transform the y first, and then if it does not fix the problem, then we transform the x. So here the transform y is we first do that because the correcting one direction of departure from assumptions by that correcting that, the other departure may also be corrected. So if you correct for the non-constant one, then the nonlinear problem may be solved. And if non-constant variance problem is only solved, but it does not fix the nonlinear problem, then we transform the x. And for example, scatter problem y and x, here we have the nonlinear pattern. And then the residual plot is, so here we have increased the fan shape of the residual plots. And this means that the non-constant variance. And then if we change the y to log y, then this hypothetical example, it is solved. So when you transform initially in the SAS, you need to create the new variable in the data step. So you need to create a y log equal to log of y. So you can make a new variable. So I will talk about the unusual points in the next video.